The title of my talk is Low Energy Nuclear Reactions Induced by Photon Emission. This is work done in collaboration with Ankit Kumar, Raj Pala, KP Rajiv and K. Ramkumar. First, a few introductory remarks. Low energy nuclear reactions. At low energies, nuclear fusion is strongly suppressed due to Coulomb repulsion. Yet, experimentalists have claimed that fusion reactions are observed in condensed matter medium. In a recent paper submitted to the Indian journal Parmana, we proposed a mechanism by which this process can happen in principle. The mechanism involves a perturbation which we assumed is provided by a photon field. The perturbation can come in a variety of ways. This is just one assumption we made in order to get started. We assumed an incident beam of photons at infrared frequencies which induces the reaction. It need not be infrared frequencies, it can be higher frequencies, and the results will depend on the flux of the photon beam and the frequency. For simplicity, we considered a specific reaction, although the idea is valid in general and can be applied to a wide range of fusion reactions. We considered one of the simplest reactions in which hydrogen and deuteron undergoes a fusion to form helium-3. This reaction is different from the standard reaction, the standard fusion reaction that is studied, for example, in astrophysics, in applications to stars. In that case, you just have a hydrogen and deuteron fusion to form helium-3 with emission of a photon. So this standard reaction gets dominant contributions from the first order in perturbation theory, because first order in perturbation theory because it has to emit one gamma. So you need electromagnetic interactions at first order. Here you have two photons involved. So therefore you need to go into the second order in perturbation theory in order to compute this reaction. This reaction is zero at first order in perturbation theory. So this reaction is qualitatively different from this reaction. So you want to see whether going to a reaction which is starts at a higher order in perturbation theory, we can get some enhancement in the rates. It is possible in principle. It is seen in other particle physics reactions. The basic idea we had was that after interaction with the photon, the system D plus H is no longer an eigenstate of the unperturbed Hamiltonian. We can expand the state now in terms of all eigenstates of the unperturbed Hamiltonian with energies ranging all the way up to infinity. So due to this presence of very high energy states, which can in principle contribute to this process, it is possible that the Coulomb barrier can be overcome. Does this really work? After submitting this paper, we continue to work on this and did a detailed calculation using nuclear and molecular potential models to see if we actually missed something. We realized that indeed we did miss some very important aspects of the problem. In particular, we should say that in the paper that was submitted, the medium did not play any important role, and experimentalists have been claiming that medium is necessary. Fortunately, if you think about those carefully, the problems that we actually found can actually be solved. They have a solution. And I'll try to give a proof of principle that this theoretical structure has the potential to explain the phenomena of low energy nuclear reactions. So we are now proposing, we are writing a new paper, and in that we are proposing a generalized mechanism. We first of all realized that we do not really require an incident photon. We can simply emit a photon. That also acts as a required perturbation. And the photon can be emitted with energy up to the Q value of the process. Q value is basically the energy, the maximum energy that can be released in this particular reaction. And as we'll see, The mechanism actually now we have realized actually that the mechanism works only inside a condensed matter medium, else it actually fails. This is very much consistent with what the experimentalists have been claiming. We will now demonstrate this idea by considering the process hydrogen plus deuteron going into helium-3 with the emission of two photons with energies omega 1 and omega 2. One of these at least have to have a fairly high energy of the order of the Q value of the process. I should point out, so now let's think about how we will eventually apply this to experiments. We must point out that we are not claiming that the experiments that have seen this phenomena are necessarily seeing hydrogen and deuteron fusion. We are using this only as a demonstration. It was necessary for us to do the simple calculation first in order to understand the issues that are involved. Only then we can understand how to solve them. So we are using this fusion only as a demonstration. And we now claim that hydrogen and deuteron fusion can take place at observable rates in a medium given the right circumstances. Observable rates means that if you load the system with enough hydrogen and deuteron, then over a reasonable time it is in principle observable. Now at this point we are not directly making contact with real experiments, and also we need right circumstances. I will explain what those are. It is possible that, so we are not claiming necessarily that this particular fusion mechanism is seen. The right circumstances may not have been met in the data, in the experiments for this particular reaction to occur, and maybe the reaction that do occur have a larger rate compared to this particular reaction. But this is just used as a simple process for demonstration. Application to real experiments is postponed to future work. The mechanism is general and can be applied to a wide range of processes. We just need to specify the nature of perturbation, which need not be caused by a real photon. A simple generalization is that it may be a virtual photon. For example, instead of a real photon, you may emit a photon and it may go into electron-positron pair, or the photon may actually be absorbed collide with another ion and may transfer the energy to the ion. Those would be virtual photons. The final state also need not involve a photon. We invite all experimentalists to tell us the nature of process they are considering. In particular, what nuclear reactions are potentially taking place in their experiments. What are the initial and final states? What medium characteristics are required? Given that it should be possible for us to generalize our calculation to a wide range of experimental conditions. Let me now start by giving some technical theoretical details of the calculation. The Hamiltonian for this process can be written as the unperturbed Hamiltonian plus the interacting Hamiltonian, the perturbation. Where the unperturbed Hamiltonian, H0, we are considering two-body fusion, two-body reaction. I mean the initial state has two nuclei. K1 and K2 are the kinetic energies of the two nuclei, and then we have the potential energies. The potential contains several terms. There is the Coulomb barrier. There is the screening potential due to electrons. We will need to consider non-zero angular momentum states. So there is this angular momentum term. Then there's a nuclear potential. There's nuclear potential between H and D. I'm sorry. So this is the molecular potential between H and D. And then we have the nuclear potential relevant for the fusion of hydrogen and deuteron to form helium-3. In writing down this potential, we have also assumed spherical symmetry, which may not actually be valid in the medium. Medium does not necessarily have spherical symmetry, and it may have some more complicated symmetry structure. In fact, it may not have any symmetry at all if you consider a non-crystalline medium or you fill up the medium with defects. So this may require generalization. The potentials. This is the nuclear potential for low A nuclei. So a convenient form is like this, where this distance scale we take to the order of 1.8 Fermis, and the potential depth we took to be about 55 million electron volts. Then we have this molecular potential, for which we have this standard formula which is used. And here you can actually determine the D, these parameters D, A. This is the Morse potential actually. These parameters D, A and Rm can be determined from data. We use these parameters. These are actually slightly different. Actually, the D parameter is slightly higher than what comes out from the data. Then there's also the screening potential, which we took to be like this. This also deviates a bit from the standard screening term, which is typically e to the power minus r by r naught. The reason we took these deviations was because we are using both of these potentials simultaneously. And if you were to fit the experimental data properly, then you would not have this term. You will have only this one. If you include both, then you will not get the right binding energies for the DH molecule. So we adjusted these two parameters a bit. So instead of r by r naught, we took r square by r naught square, and we adjusted D a bit so that we can get, reasonable potential which agrees with the standard potential. That was the basic idea. We can do better by, taking this formula and fitting it at low distances to the screened Coulomb potential. One can do all that, or simply Coulomb potential in fact. But actually, those minor details will play no role in our analysis. Those are just totally irrelevant. They'll change the result by a factor of order unity, which is not relevant. We are talking here about trying to demonstrate the principle, and we are only interested in order of magnitude estimates. So these details are almost irrelevant, as we'll see. And we have verified that the nuclear and molecular potentials lead to the correct ground state for the DH molecule for the helium-3 nucleus. It also gives the correct fusion cross-section at keV energies for the standard process, deuteron hydrogen fusion. This is verified by using the standard formula. Sigma is equal to S by E times the barrier penetration formula, which is a standard term that you are familiar with. And our calculation gives a result which is in very good agreement with these formulas. In fact, this formula does not include screening, so we get a slightly higher fusion rate, which is actually consistent with the fact that we are actually including screening. So now, in order to perform the calculation, we first need to determine the eigenstates of the unperturbed Hamiltonian, H0. We will need three types of eigenstates: the initial state, the final state, and a tower of intermediate states. All of these are eigenstates of the unperturbed Hamiltonian. Next, we need to determine the effect of the perturbation. So just to pictorially see these eigenstates, basically this sort of represents the potential in the medium, or the potential between deuteron and hydrogen ions, and this represents the nuclear potential, which is very deep. So you have these molecular states. Here I've sort of tried to indicate this as the ground state, and then the tower of higher energy states, and beyond a certain energy these just become free. And then there are these nuclear states which are very deep. Actually, for this particular system there's only one state. In fact, none of these actually exist. I've just schematically shown that in principle they are there. Only one is known to exist, although near the top, actually we have not found any state without model. So let's say that there's no state exists. Only the free states will exist on the top of the Coulomb barrier. So we have eigenstates which are peaked in the two regions, in the regions of two potential wells. So this eigenstate, for example, the eigenfunction will peak out here and then decay rapidly out here. Yeah, of course, this is the Coulomb barrier, and through the Coulomb barrier, this has to decay very rapidly. So the amplitude becomes very, very small out here, and that is the problem that we're trying to face. And similarly, the nuclear eigenstates are peaked in this region and they decay very rapidly in this well. So the problem that we are trying to face is that you have initial state of this kind with this energy, which has to make a transition into a nuclear state of this energy. And we are claiming that it does so by superposition with all of these states. So let's see how that works. So let us first take a look at our calculated molecular wave function. This is the molecular wave function. This is the psi, the wave function psi is really u of r divided by r times the spherical harmonics. In this case, actually, this is L equals 0. So there's no spherical harmonic in this case, or is y0 actually. This is our initial state. Then we have the nuclear wave function for helium-3. Again, this is L equals 0 wave function, S wave. So this has such a form. Here, I mean, in both of these cases, we are showing this in atomic units. So this is our final state. The process is induced by electromagnetic perturbation. So the perturbative Hamiltonian or the interaction Hamiltonian is standard. You have this term, the electromagnetic field, which is given by this. These are basically annihilation and creation operators times this free photon amplitude, and there's a volume factor and all that. This is omega is the frequency, k is the wave number, this epsilon is the polarizations. So times the momentum of particle 1, which we can take to be the proton in our case. This is the position of particle 1, which is a proton, as I said. So Z1 is the charge of proton, M1 is the mass of proton. Similarly, we have a term corresponding to deuteron. Then we have a magnetic momentum. Here again, we have to include magnetic momentum for proton as well as deuteron. We will actually neglect the neutron term. This proton term will suffice for us. All these other terms just add up complexity to the calculation but play no essential role. They'll give a small correction. So we'll just ignore them for our analysis. So, and B is the magnetic field. So, and sigma are the Pauli spin matrices which will come along because we are considering magnetic moment interaction. MP is the mass of the proton. So there are two amplitudes that contribute at this order. The first amplitude is you have this deuteron and hydrogen initial states with energy EI, which is supposed to be small. I emit a photon from hydrogen, and I can also do that from deuteron. Both those terms have to be included. Once this photon is emitted, this system goes into a state which is not an eigenstate of the Hamiltonian or the unperturbed Hamiltonian. You expand the state as a superposition of all states. That is where this sum comes up. So you have states with energy En, and we have to sum over all energies. Then we have this second interaction in which another photon gets emitted. Then for each state, we then determine the overlap of that state with the final helium-3 nuclear state, including the effect of the perturbation, and then we sum over all the states. So that is what the calculation actually involves. The second amplitude is similar to this, except that the photon with energy photon energy E2, E gamma 2, can come from the first vertex, and the photon with energy E gamma 1 can come from the second vertex. So both these processes have to be included. So this is done within the framework of second order time dependent perturbation theory. The theoretical framework is standard, discussed in any standard textbooks, Merz-Parker or Sakurai. Due to the presence of two photons, we need to go to second order, as I already said. The transition amplitude formula is standard, taken directly from these books. So you have the initial state, the perturbation Hamiltonian, the intermediate state, then this energy exponents, then the intermediate state, then the interaction Hamiltonian overlaps it with the final state, and again this integral over time, and then we sum over all intermediate states. Initial state is the D plus H state, final state is the helium-3 state. And this is just the same formula copied again. I just want to say that we need to sum over all energies of the intermediate states. So the sum goes over all energies up to infinity. Because of this high energies involved, there is a possibility of overcoming the Coulomb potential barrier, which has been one of the major problems with these fusion reactions. Some more details. The transition that we'll consider is between an initial state L equal to 0 to final state which is also L equal to 0, the initial molecular state to the final nuclear state. The intermediate states will be taken to be L equal to 1 because that is what is required to have a photon transition, at leading order at least. At higher orders you can have something more. We need to sum over final state photon polarizations. We need to also integrate over the angular distributions of the emitted photons. And finally, we need to average over the initial spin states of nuclei. Calculation. All terms in the interaction Hamiltonian contribute to both the matrix elements. That is this initial to intermediate state matrix element, intermediate state to final state matrix element. For illustration, we shall keep only the magnetic moment term in the molecular matrix element, and for the nuclear matrix element, we'll keep the remaining terms. This calculation has been evolving, and slowly we are learning what is dominant and what is not dominant. At this stage, it seems that almost all of them will actually contribute non-negligibly, and we have to possibly include them. And but for an order of magnitude, what we are doing is actually perfectly reasonable. So the detailed formula for the transition amplitude can be written as follows. You don't need to, well, this is E squared process. There are two electromagnetic interactions involved. There are this Gp is the magnetic moment of the photon, the proton, sorry. And so we end up with such a result where this is contains all the matrix elements, the amplitude. So the amplitude is given as sum over all the energy states, and we have the initial state to the intermediate state and intermediate state to the final state. So now this is okay, first let me just mention that the second amplitude basically involves K1 change to K2 and omega-1 change to omega-2. There's also this spin matrix element, which involves the overlap of the spin of the proton. Okay, so this is the spin of the initial proton, and this is the spin of the proton in the intermediate state. Okay, so now it's interesting to see this in more detail. We have this energy denominator, which is essentially arising because in the initial state we did not have enough energy, and yet we emitted a photon. And we are claiming that the intermediate state can have this energy En, which we are taking to be relatively large. So Ei is very small, En is large, and we also would like to have this photon energy to be relatively large. So therefore, this energy denominator is relatively large. So this is the price we have to pay for sort of violating the energy conservation at that vertex. So that is perfectly allowed. It is just the total energy that has to be conserved. This is time-dependent perturbation theory. So the energy conservation does not necessarily apply at each vertex. We can violate it for a small time interval prescribed by the uncertainty principle, and the price we pay is just this energy denominator given out here. Now look at this matrix element carefully. This is the overlap of the initial state with the intermediate state. In many calculations, this overlap is computed assuming a dipole approximation in which this factor is set equal to unity. In fact, in that particular, this is a magnetic moment interaction. When you set it equal to unity, this overlap actually might be zero because this state is actually orthogonal to this. So we may have to include some other interaction for that purpose in this case. However, K1 is large in the present case. We are emitting a photon of MeV energies in this case. So K1 is actually quite large. And if you look at this carefully, you will find that it is not a good approximation to set this exponential factor to unity. In fact, this exponential factor is very rapidly oscillating. Now, if you had some, in fact, that is very, very important for us. If we had some factor out here, which will allow this to be non-zero, but this factor was not showing rapid oscillations, it was showing slow variation with R. Now, N shows very rapid oscillations because it is a high energy wave function. I varies relatively slowly. Then this overlap will not be very sizable. In fact, this will be highly suppressed. It is the presence of this very rapidly oscillating function out here that allows this overlap to be sizable for a small range of Kns corresponding to this state. So let us continue. So now for the nuclear matrix element, we can use this approximation that this is set to 1. This is called the dipole approximation. This is valid for nuclear matrix element, but not for the molecular matrix element. For the latter, we have kept all terms to all orders. The molecular matrix element I to n, it involves overlap with low energy wave function I with a high energy wave function n. This overlap will be very small. We in fact found that by explicit calculations, unless HI involves some high energy process. This is provided by emission of a high energy photon in our case. We can emit a photon with energy up to Q value of the process, which is about 5.4 MeV in our case. This allows this matrix element to be significant for a small range of En intermediate state energies. Here is, for example, the intermediate state wave function for energy corresponding to 1 kilo electron volts, where R is in atomic units. So this is just 1 Bohr radius. So you see these rapid oscillations. If you now look at the molecular matrix element, this is I to n with this rapidly varying exponential. We do find a significant value in the neighborhood of Kn given by this. So this corresponds to energy of the proton-neutron system, the effective energy of the proton-neutron system of the order of 8 to 9,000 electron volts. So about almost 9 kilo electron volts. So in this range, this matrix element, okay, there are some technical details, I'm just giving some rough ideas, can be quite sizable, okay, for the unity. And then as you go beyond this, it actually decays rapidly to zero, and below this also it decays rapidly to zero. So because we have sizable overlap out here and the Coulomb barrier is not very prohibitive in these energies, we have the hope of getting a sizable fusion cross-section or reaction rate. The nuclear matrix element involves a Coulomb tunneling factor and the nuclear length scales, few Fermis. The tunneling factor corresponds to energy scale En, which is relatively large due to high energy photon emission. So Kn is given by this. Energies of the order of keV, keV, 10 keV. And over this energy that I just showed you, here I'm showing you this nuclear matrix element. It is small, but not very small. This actually includes, this is basically containing the tunneling barrier penetration contribution. So that is why it's small. And also the nuclear length scales. We need to sum our intermediate state energies. This goes up to infinite energies. We first perform this sum by assuming that intermediate states can be approximated as free particle states at large r. This is a good approximation in free space, but this may not be valid quite in the medium. That will be very important for us. So let us just do this by making this assumption. This phi is some sort of phase shift which is necessarily there, and we have this wave number times r at large r. So we now insert this wave function for intermediate states. We compute the molecular and nuclear matrix elements, and here I'm showing you the integral, the final energy integral over En with some upper cutoff. In this range, the molecular matrix element was almost zero. We got no contribution. Out here it picked up. We start getting contribution. It picked up to a large value. And then remarkably enough, it beautifully cancels out and goes to zero again. So the integral goes to zero as we increase the upper limit on energy, although it becomes relatively large at some energy cutoffs. Hence, the calculation fails to give a significant result if we use free space wave function. This is the last step that we needed. If this succeeded, we would be in business, but this failed. The energy integral adds up to zero. There's a beautiful superposition which simply cancels the contribution that we obtained out here. So we actually have a failure of our proposal using free space wave functions. This is probably good, because this null result is perhaps consistent with what is seen experimentally. The process takes place only in medium and also requires special circumstances, as experimentalists have now been telling us for many, many years. Let us see how we can evade this null result. We see several possibilities, perhaps some even in free space, although whether they are realized or not is a question, and I don't know the answer to that as yet. We need to work more. Possible solutions. Let us understand how we can possibly solve this problem. The cancellation occurs since we have a very rapidly oscillating molecular matrix element multiplied by a relatively slowly varying function. So we see that this molecular matrix element over some range shows very rapid oscillations. I should clarify that this is for a particular choice of emitted photon energy, and we actually have to integrate over all photon energies. That integration actually over matrix element square, so it's an incoherent integration. So as we change the photon energy, this bump will keep shifting to lower and lower energies. Here I've kept almost close to the maximal energy that we are permitted to have in this case. So we can actually scan a wide range of energies. In fact, it'll be good to actually go over all energies up to kilo electron volts, because up to that point we can get significant contributions and the barrier penetration factor is not too small. Okay, so this is the problem is that this is very rapidly oscillating multiplied by a slowly varying factor, and that is why actually it all cancels out. We need to find an additional contribution which varies equally rapidly. If there's something, some additional thing which shows a very, rapid bump out here and then just goes to zero, that'll do it. Let us first suggest a nuclear solution. This can in principle work even without requiring medium. The process can get substantial enhancement if there exists a possibility of resonant tunneling at some high energy within the range Kn less than the emitted photon energy times this m2 by m. m2 is just the mass of the second particle, in our case deuteron. M is the total mass, mp plus m deuteron. So we need a resonant state in this energy range specified by this limit with a narrow width, so that the amplitude changes at a rate comparable to the molecular matrix element. So we need some sort of a resonant contribution which sort of goes like this, somewhere in this range, rises at roughly the same rate. It need not be exactly same, it could be a bit slower also. It could even be like this, something like this. That'll also work. But something, so that would mean, with a width of the order of 100 electron volts something or less, not much larger than 100 electron volts. That'll work. So that'll give you a fairly large contribution. The question is whether such a resonance exists or not, and for which reactions it exists. Now we go to possible solutions involving medium. The wave functions n, which we assume to be the free space wave functions, in medium they can be very complicated. At high energies, we expect scattering states in the medium, which actually will deviate a lot from the free space states, free space scattering states, as well as localized states. By localized states, we mean that the wave function is non-zero only over a small spatial region and then decays very rapidly beyond that. In crystalline solids, the states would form band structure. Now this may lead to allowed bands separated by forbidden bands. In case that does happen, we will again get a large effect. For the allowed bands, the amplitude may change relatively rapidly. Then again we'll get a large effect. The band structure that we are familiar with is the one associated with electronic states. Here we are not talking about that. We are interested in the wave functions of ions in the medium, with energies in the range keV or higher. We expect that these will also experience periodic potential due to the radicides and may form band structure. This has never been studied before, and something that we intend to do soon to understand the nature of these states. So if that band structure shows variation, anything comparable with what I've shown you in the nuclear matrix element, for example, it decays at some point and there's a small width between two bands, they'll do it. They'll lead to the effect that we are looking for. Other solutions involving medium. The scattering states, so these are states which are actually do not decay, they extend over larger distances. Actually in medium, all states will decay beyond a certain distance. But these are states which are, somewhat more extended. Okay, I should clarify that actually when you form bands, those states are actually extending all over the medium. But the scattering states are the ones which will actually scatter from the medium particles also. Those states are not, the band structure states are not scattering from the medium particles. So these scattering states, they will also display sort of threshold effects. At certain energies, we may reach a threshold to knock out an ion from the lattice or a bound electron from its shell. At these energies, the scattering state amplitude will show a sudden change. Such behavior is seen in all threshold effects. These can also lead to substantial contributions. Finally, something that we are quite excited about, if we add impurities in the crystalline structure, we expect appearance of localized states, that is states which are localized in space. These may be widely separated in energy from one another. This phenomenon is called Anderson localization for electronic wave functions. And the same may happen for the wave functions of ions that we are interested in. For such states, we expect a large effect due to the large energy gap. Because of the large energy gap, the cancellation will only be partial. Note that the wave function modification that is required only at large distances, order atomic length scales. In that, the experimentalist has some control over what can be done, and hence the mechanism has a good chance to work out. Let me give you a toy model which is tentative. The idea seems to work intuitively, but the mathematical details have still to be worked out. We assume a medium with cubic lattice. This is what I'm showing out here. Each side out here has an atom of large A and offers a repulsive potential to the nuclei. In the neighborhood of the Z, X and Y axis, the potential actually vanishes. So in this, along this axis, there is no potential, there is no atoms out here. Or the potential is relatively weak, it's uniform, let's say. The wave function shows a free particle behavior because of the uniform potential. It shows a free particle behavior along the Z axis, but it is localized. We assume that it's localized in these other directions. So the Z dependence of the wave function will be such that it's a free particle for large Z, small rho. This is using cylindrical coordinates, and it goes to 0 at large rho. In the region corresponding to Coulomb repulsion close to the nuclei, we expect an exponential suppression in the Z dependence. This is the Coulomb repulsion factor. And the wave function can also be extended inside the nucleus. So we have this free particle wave function at large Z, small rho. Now when we compute the molecular matrix element, which is given out here, we assume that the K1 points close to the Z direction. So K1 dot R, this is the photon wave number, wave vector, is K1Z. Then when we compute the molecular matrix element, you have this overlap of free particle wave function with this factor, which can now be written in this form. You end up finding this overlap equal to K minus this times R cosine theta times the initial wave function. Then you need to do an integral over cosine theta. This yields a sinusoidal function over delta K, where delta K is basically this difference. Now we see that the matrix element is dominant at delta K equals 0. And the energy integral we have verified does not vanish. In fact, it gives a very large contribution. So for this very simple toy model case, we actually get a very large contribution. Whether this toy model potential can be realized or not is a question. And that's why I like to see what experimentalists are actually able to set up in their laboratories. In any case, with this particular toy model, we are able to get observable rates for the process. Reaction rate per particle is of the order of 10 to the minus 14 per second, which is not small at all. This is very preliminary, assuming the toy model can be realized, and I have also calculated the rate sort of roughly. The more details will be presented in the paper later on. So conclusions: nuclear reactions at low energies are possible. We have considered a simple example only for illustration. This may not be the most favorable process and requires special experimental conditions. We invite collaboration with experimentalists so that we can estimate the reaction rates for realistic experimental situations. Thank you very much. Sorry that I went a little bit over my time.